Thank you. Well, thank you for coming after the dinner yesterday night. Okay? I want to show you that I'm doing, say, some effort to trying to understand this funny thing we call compact. And I would put this in the context of kinks, lumps, cue balls, and branes. I will first do some motivations, then I will talk on kinks, lumps, and compactons. I will show how I can put kinks and lumps in the compact, scenario. Then I will talk a little bit on cue balls and branes, too. Okay? Motivations. I'm talking about, defect structure or localized structure, which I can see like this one. This may be a spin system where I have a spin up and a spin down, and this is a defect. This is the name of defect. But I can see this in this way, changing colors. And in this context, we call this an interface, which separates between somehow distinct regions in space. Okay? And those kind of solutions can be kinks, which are topological, lumps, which are non-topological, and the compactons, which are kinks or lumps that lives in a compact support. Okay? Kinks, another motivation. Okay, this is a paper by people working on the IBM Zurich laboratory. Okay, this is at the nanoscale. This is they call it a domain wall. Okay, but it's a kink. A kink is a domain wall immersed in a larger dimension. You have, the magnetization here in this direction, the magnetization there in the other direction. They goes in this way here. Okay, this is a kink. But this kink may be dynamical. I'm not going to talk about dynamics, but if you put a current here, so you can flip, polarity. Okay? The reason for doing this is obvious, okay? Or the motivation. This is a, home motivation. If you study, species, and if the color here represents different species, and this is an interface. This is a kink-like solution, an interface here. And this snapshot here is for, 3 species, 4 species, 5 species, and 7 species. When you increase the number of, people playing around, you get, the interface, get some internal structure. So there is a dynamic inside the interface. Another motivation, for branes is, for Braneworld, is motivated by string, the presence of extra dimensions. In the paper by Handelsundrum, the second paper by Handelsundrum, where the extra dimension is an infinity dimension. Okay? The first work is we call the scenario, thin brain scenario, which is this one here. There is kind of cusp here. Okay? But if you add scalar field, you make the brain was smoothly here. So we call this thick brain scenario. So since I'm going to talk about scalar fields, and I will put scalar field on this scenario, so I'm going to talk about thick brain. Okay? You can do this for holographic dimension. The holographic dimension is 1 dimension. I need 1 dimension. My physics is always in the real line, 1 dimension. But my 1 dimension may be X, maybe the extra dimension, maybe the holographic dimension, maybe the R coordinates in, say, black hole scenarios, etc., etc. Another motivation, because I'm talking about compactons, so I have to change the kinematics. So the main motivation for this comes from cosmology. So the universe is in accelerating expansion. So people, they say, perhaps the two main, say, stream are changing GR, changing R to F of R, or changing kinematics. In a field theory, X for me is this. Okay? This is the kinetic energy. Okay? Changing this to F of X. And we need this to find compact solution. Another motivation is the compact. This is a semi-compact, skyrmion-like structure. We can control the, say, internal core of the skyrmion, which is, say, this funny structure here. Okay, this is a planar structure. I'm not going to talk on this. Okay, Kinks, lumps, very briefly. This is my field theory. I'm always with one field in one spatial dimension. Okay, it's very easy, 1 plus 1 dimension. This is my model, and I look for a static solution. So the equation of motion is this one. This is an EDO. Okay, I can model with choosing V properly. So if I choose V properly, I can have kinks, which are solutions that are different, asymptotically different. This is the reason for the topological property of the kink, which say kind of smooth step, okay? Or it can be lump, which is this one, okay? With this property, okay? And a compact is the same thing, but in a compact space. Okay? I'll give you an example. See, I'll call this the 5-4 model. This is my standard model. It is a standard model, okay? If you have this potential, this is the potential. I have two minimum states here. So the solution, the topological solution, in this case, the solution explicitly is the hyperbolic tangent. And it reminds you of these two minimum states, spin up or spin down, red or blue, okay? And, okay, I have two parameters here and there. They control the amplitude and the width of my solution. They control the physics of my solution. But I'm putting it one because I'm doing classical physics. I just want to show you that they appear, okay? I'm not doing quantum physics here. If I turn the potential around, the other way, then I have a lump solution. In this case, for this potential, explicit potential, the solution is hyperbolic second. Okay? This is a, say, is multi-step, this is, say, a kind of, it's a lump solution. Okay? But they appear in different physical scenarios. Because you see that here, that this is a kind of two-body attractive interaction. So you have kinks. This is you change the sign, so this is a two-body repulsive interaction. So this is stable, and this is not stable. In this context, but that solution may be stable, this may be stable, this may be unstable in other contexts. For instance, in optical fibers, okay? People call this say, bright solids, because this is the electrical field concentrated in a region which moves like a solid and is stable. And this is a kind of the inverse, kind of a dark solid, the absence of light in a point that goes. This is hard to find there. This is easier to find there. With the contrary of what happened here in filter. Okay? And compact. So before you send me to jail, I will stay here for 2 minutes, okay? But you have to change dynamics. This is, say, the velocity to the power 4 in a mechanical system. Okay? I need this. The signal here is to keep the energy well defined. So, but if I look for the equation of motion for a static solution, I get this one now. Okay? And this allows, in this case, for this potential being the 5-force potential, the same potential, the solution is the sine of x. And the sine of x goes to 1 here at pi over 2, okay? So this is a compact solution. The solution is everywhere, but from here on, it's the minimum state, okay? The energy density of this solution is concentrated in this compact, okay? Super. To do this, since the potential is a smooth function, and since you have a problem here with the derivative of this function, you need this. This will help you to not have a problem in the equation of motion. This is the reason why you need to change, say, the kinematics to have a compact. Compacton was first appeared in this paper in 1993, and then there is a paper by Sodano also here in the same year. It's appeared in context of integrable model, KdV equation. They changed the nonlinear dispersion. You need nonlinearity, and you need nonlinear dispersions too. Okay. And why am I doing this? Say this crazy, say curious thing. Because we invented here a new way to approach a compact solution, which is controlled by the potential. We change the potential. In this paper, we have, say, 2 examples. One driven by alpha, which is a real parameter, and the other driven by n, which is an integer parameter. The model with n is here, explicitly here. So if n is 1, this is the 5-force model. So I'm getting an extension. You see what I'm doing? I say, modifying the way the field self-interact. Okay? And we noted, why this? What is the motivation? We know that the solution, the effect solution, goes to the minimum for the potential asymptotically, exponentially. And the way it goes depends on the mass of the elementary excitations you have there. So you said, let us change the mass, make the mass increase. It is still going, say, asymptotically, exponentially, but if the mass is we are kind of compactifying the solution. That's the idea. It's as simple as that. You see, the mass of this model is controlled by n. So when n goes to infinite, the solution, say, shrinks to compact space. Okay? And I'll show this here for you. The equation of motion of that model is this. We have to solve it numerically because we cannot get solution for arbitrary n. So we did it. This is the potential. This first line here is the 5-4 potential. Okay? So when n increases, you are getting to a flat, okay, line here with the minimum here. Okay, this is the parameter is doing this. And the solution, which is the kink, the hyperbolic tangent, is going to concentrate around this compact interval. And the energy density, we plot here, which is, say, localized, but it goes exponentially to 0, it's going to concentrate, okay, in this region, And here, when you have a field theory, you have, let me say, put this. If you have a field theory, with the say, you have a potential, and you find a solution, a static solution, phi of x, you can study stability. Say, it's the way to go to quantum effect. When you study stability, you say that your field of phi of x is this field phi plus a fluctuation. This is a standard scenario, okay? And then you go, since your problem nonlinear, you go to first order in the fluctuation, okay? So in this case, there is a nice picture here because you get to this always. The equation of motion, which for this the fluctuation is this one. U of x okay. If this is sum of tan of x and cos omega. Since your solution is static, so you can always separate this equation. So you solve it for time, and this is, say, the standard time evolution. Okay, I'm putting the cos of omega t. And this is omega n t. Okay? So this is quantum mechanics. Okay? So this is Hamiltonian. Okay. And this potential, since the equation of motion depends on the derivative of the potential, and I go first order, this potential here is the second derivative of the potential that you put in your field theory, calculated as the solution, with a static solution. So this is my U of x. And you always, get, there is a way around. You can go from here to there. There is one-by-one correspondence. So you can reconstruct a field theory model starting from a supersymmetric quantum mechanics. Because this, you can show that this environment has a, say, supersymmetric scenario in the sense of quantum mechanics, using QM. Okay? This potential I will call the stability potential. This is the stability potential. Excuse me? I don't know, because I always look for static solutions. And I see no motivation for looking for, say, a more general solution yet. My static solution, in fact, is not static because I'm sitting on it. I'm choosing a frame where I see no time evolution. Say, but I can do a Lorentz boost and make it goes like a, say, traveling wave. Okay? But this is a trivial, say, time evolution. I see nowhere in the literature people working on, say, two solutions depending on x and time altogether. And in general, thing that we do here, we need, say, ideal equations. So if you want to say partial differential equations, things are a little bit complicated. Okay? You are going to talk to them. Sure. The usual picture. It's in, say, Hajaraman book, for instance. Okay. If it is, since what Sancho is asking me, if this guy here, this is the energy of my quantum mechanical, but it gets squared. So if the energy has positive angular, saying another way, if this Hamiltonian is a non-negative operator, So the system is stable because these are all positive. The square root of a positive number is positive. Yeah. If you have a single, but you just need one, a single negative bound state, so you will have a problem because the square root will give you an imaginary thing. If you make the cost of imaginary thing becomes a hyperbolic cost, so the solution is not localized, proved, you say. Okay? This is the usual contest. You should discount this time, okay? In my foot. Okay. We have coffee break time. Okay? No, please. Please. Oh. No, it can be real. But we are using integer because it's easier to see, easier to convince people that 5, 4, 5, 6, 5, okay? It's not 3.5 or say 2.2, but it can be real. Sure. Okay, this is when you do this for that potential, you get this, I will call this the stability potential. My stability potential is this. In the 5-force model, the stability potential is the modified Posh-Taylor potential that I guess everyone here knows. It's a potential this way. It has two bound states. One is the zero mode that is always there because of translational invariance of the theory in another state there. Okay? And then a continuum state. In this case, you see that you have a kind of a well, which is going up, until when the solution is compactified, you have not the outside. So the stability potential should be like a harmonic oscillator, or the Posh-Taylor potential is the second parabolic. So it gets states and states, bound states here. And here plotted the number of bound states. You cannot read it. Here is the number of bound states in function of n. As we increase n, the well of the potential increases, and we are getting bound state, bound state, bound state. Okay? And it goes up almost linearly, I could say. And this has a distinct collective behavior. This is the first physical, say, good thing that I can say about compactons. Compactons, solitons, if you put a soliton near to the other, they interact because they have a tail. Okay? Compact, no. They form an ideal gas. So the collective behavior of compacts is completely different from the collective behavior of soliton or this kind. Please. Yeah, just good. What kind of physics? Okay, we are looking for that too. I'm showing that they have, say, a collective different contest. If you shake topological solution or a vortex or a what kind of physics I can do with the compactor? You're asking me this? This is a hard thing. If you look at the compact, if you change the kinematics, for instance, okay, I don't know any physical system that behaves in this way. Also, we are studying this, so be patient with me. We are studying this. We don't know too much, okay? We are looking for something. And I'd say if there are some physical systems that where this kind of thing may make, say, a game, they will be a different game. Okay? If you shake a kink, the kink irradiates energy. If you shake a compactor, it does not irradiate energy. It assesses the bound status here. And it returns. This is different. But where do I put the physical scenario for me to put in this? There is a better way. Because we are approaching compactons through standard dynamics. I'm showing this. This is an example. So we need, say, 5 to the 1,000 self-interaction. Say, I could say 5 forces is a 2-body interaction. So 5, 6 a 3-body. We need to say 100 body self-interaction. I don't know a physical system where I can use this. So I circumvent the problem of doing, say, modify the kinematics. But I need a self-interaction. Okay? But let's go a little, okay? Let's go a little further on this. Compact lumps. Compact are similar to compact kinks. We showed in this paper that the same potential that we invented there for making the kink compactify, we can do it for making the lump compactify. The same thing. But I have something that I like, I want to show you. This is a model. This is an analytical solution. I like this model because it's the perfect word. It's all analytical. The potential, the solution, the stability, etc. I can find everything analytical. Remember the potential to have lumps, I have to change the way they interact. Okay? So this is it's just funny because you see, if you Q is 3, 5, 7, okay? For Q is equal to 3 or 5 or 7, I have compacton. I do not have compacton and Q goes to infinite. I have compacts for every value of Q. We invented this model, and this is a solution. Okay, you see the solution is going, say, to 0 in the compact space. This is the potential, the stability potential. The stability potential for Q3, for Q5, for Q7, they all goes to infinity, say. The bound state, the states are all bound states. There are no scattering states in this problem. Okay? So, everything, I found the bound state. You see that the bound state are here. So understand. If n is 0, you get a negative number here. So the first bound state is under the 0, signaling instability because they are lump. Lump are unstable in the field theory context. So I always have, because I always have the 0 mode, and I have a state. But this is all analytical. I didn't write it, but it's analytical everywhere. Okay? I can do this for kinks. I can do this in an interesting scenario. If I write my potential in this way, as the square of W, I take a function of phi, I differentiate it, squared it, okay? If my potential is this, the second order equation of motion, okay, can be solved by first order difference. This is supersymmetry behind. This is a superpotential W. So you get a nicer environment. It helps a lot to solve first order differential equation, then solving, okay? And I can do for kinks, this is well known. We can do for compact kinks too. So although I am changing this, adding funny self-interaction terms for that, I can do in a supersymmetric environment. I'm telling you this. In some cases, okay, for the example I gave with the potential driven by N, I can do it as it is. So this state is called the BPS state. So I still have, perhaps people from string may like this, I guess. So you can use the supersymmetry. So everything is a bit easier. You can do this for kink, for compact. You cannot do this for lumps, because lumps are different. They're unstable. They are here stable. You can prove in general that the solution are stable, etc. Okay. Cue balls. Cue balls was a Coleman invention, you could say, in 85. And we are studying cue balls too. But we are studying cue balls in a very simple environment, in one dimension. Because cue balls are important for phenomenology and other things. But we are learning this. So we are studying 1 plus D. What's cue balls? Cue balls are, you need charge. So you have to make the scalar field complex, at least, at minimum. Okay, no, so I have a complex scalar field. Okay, so I have another degree of freedom. This is my charge of my field, and the charge of my field, because this is based on lump-like solution, it makes a cue balls, and the stability comes from the charge. Something like this: if the charge of your balls is lower than the charge of the elementary citation you have in your system, they cannot decay. Something like this. Okay? Because charge is conserved. So the stability problem. This problem is a little more complicated. You have time here. But time evolution is still, say, trivial. Okay? Then this sigma field is like my X field, my phi field there in the static case. So I have this potential. And when I plug this in the equation of motion, I can write an effective potential, which is this, where the contribution that comes from the time evolution is here, in the omega. Okay, the equation of motion is this one. And I have it now, in this case, 3 parameters, N, A, and omega. Okay? Omega controls the charge, controls the stability of my solution. So, and the omega is restricted to an interval. I have A here that I can use, and N that I can use. You solve this analytically also for every, say, N and A. And the solution are here. You can say, control the shape of the solution with those 2 parameters. Okay, you can make it flat here or not, or this. Okay, but this is the solution, and the solution is kind of the composition of 2 kinks, a kink and an anti-kink. In B and minus B. B is this. You see that B depends on omega. And this is a little more complicated, this scenario here, but okay, we can do analytical calculations here too. The reference informed that there were those 2 papers that we didn't know, and they do say something that we did, okay? Before, say, 86, 87. Compact cue balls. What's compact cue balls? You have this model, okay? We suggest this model where you have A here and another parameter here, S. But you see the funny way the field self-interact now, because S for us is greater than 2, okay? And you have, say, exotic self-interaction. But you have, this is the equation of motion, 3 parameters again, and you have these are the solutions. the solution are analytical solution. And I didn't. I guess it's for stability. Acho que stability requires that as, because for the cue balls, the potential has to have a very specific form. It has to have a minimum at 0 and cross 0, because the solution kind of goes there and return back, like loop-like solution. So for this, you have to control the parameters you have in your model. My collaborators are not here, but I guess it's just the motivation. It's in the paper. You can read it there if you are more curious. You see, this is not in scale. This is a standard cue ball profile, this one. Okay? You see A is the same value. Okay? Here put S3 because S should be greater than 1, and S is 1 here. But you see the scale here. This is 8. This is 8. Okay? This is 1/2 here. This is much lower. So this solution here would be here, okay? So they are much, much smaller. It's compactifying solution. So you have a compactified cue balls. Okay, how can I go to this, to Braneworld? Okay, so I will change the subject now. Okay, and this is the standard brain Handel syndrome scenario modified by the inclusion of a scalar field. What's this? This is the scalar field is here. My scalar field is here. And coupled, I don't have, say, the dilaton field here. Okay, it's coupled with this, with gravity. Okay, in this way. I have 5 dimensions. This is my metric. And this is A. We call this, you call this the warp function. This is the warp factor. This is a warp of the geometry here. One single extra dimension. Right? Okay, this is main, but it can be ADS or DS. If you make this ADS or DS, you call this bent brane. Since it is Minkowski's flat brane, so I work on flat brane scenario. The bent brane scenario is much more complicated. Okay, please. Yeah, let me tell you, this is the single extra dimension, okay? So I'm in 4 spatial dimensions, okay? So I should use, say, not Kinks anymore, okay? But this is not the case. I tell you, people, when they do this, it's not us. People that invented this Braneworld scenario, they put the restriction that A and phi only depend on the extra dimension. Both A and phi only depend on the extra dimension. So my X there is my Y now. But I'm still in 1 dimension. But this is the extra dimension. Okay? I can put this in the Z dimension and in the holographic dimension. I have some ideas on this. I got from the seminar of those people from Rio de Janeiro. Okay? And we can put this. But I am still doing kink. The kink now, it will be the source field for constructing the Braneworld scenario, for giving you the geometry. No, it's flat space-time in the inside of the brain. I'm not looking inside of the brain. Okay? I'm looking, say, from the outside in the extra dimension. This is 4 dimension now. Okay? Mu and U goes for 0, 1, 2, and 3. Okay? The equations of motion here are those. There are 3, but I have only 2 degrees of freedom. In fact, one of the equations, a consistency equation, it gives you the energy, etc. Okay? I cannot hear you. Final temperature. The energy in this scenario is 0. I don't know if I can. It's possible to show. No, not in this scenario in general. Let me go a little more, and I perhaps. This, if I choose, I did this. This is the scenario. If people who work on supergravity, they do this in supergravity, and you can find first-order equations here too. This was the motivation for us to go into, and I show you this. If the potential has this form, say you have supersymmetry in this environment. When you do not have gravity, you do not have this part. The potential. Remember, I told you the potential is the square of the superpotential. Now you have to add this contribution because you are in a, say, curved environment. So it modifies the potential. But if the potential is this, those 2 equations solve the equations of motion. It's kind of BPS state, say, for supergravity. But I'm not in the supergravity environment. But it works anyway. Okay? In this case, for solution that solve those equations, the energy is 0. The energy density, I guess, I don't know if I'm going to plot something here. But the energy, the total energy is 0. The energy density has a profile like this. It goes down and goes up and goes down. I guess I will plot this from our paper. Okay? This equation here is the equation I had in my kink-like solution. First order, you see, the derivative is proportional to. It's hard for me to turn back, but let me see. Here, this is my equation in 1 plus 1 dimension. Okay? Sorry. This is my first order differential equation. I have to solve. In the Braneworld scenario, I have my first order equation is here. It's the same. I just have it say to put these 2 in the y direction. The same. So my field theory model feeds the geometry. If I know this, I know the kink, I know phi. I plug phi here because W is W of phi. So I find, say, the geometry. Okay? And the paper that we use most are those ones. So this is a very nice paper, a longer paper, because those 2 papers. This is Goldberg-wise, Randall Sundrum. Okay? Randall Sundrum, they just said, there is a brane there. The other people said, oh, we can do this including scalar fields. So those are 2 papers, or 2 first papers on this problem. Okay? When we found the compact solution in the 1 plus 1 dimension, I asked the student, I don't know, remember. is it possible that this compact solution compactify the geometry? Then no, the answer is no. And we call this, the scenario here is a hybrid brane. What does it mean? If you take that same model, remember the model with n, it goes to 5 to 2n. Okay, the same model, the model has a, say, superpotential. So we have a first order scenario here. And the first order scenario for the brane model is here. So we can solve this. We cannot solve it analytically because you cannot solve this analytically, but you can solve it numerically. So, and using this potential, you have the solutions. We study this numerical solution. This is the 5-force potential, and the potential goes like this in the gravity scenario. The kink is the same thing, because the kink solves the first order. The scalar field solution does not see geometry. It's one dimension. This one. This is the energy density in this case. It goes like this. Okay? And this is the warp factor. What we noted that the presence of the scalar field make the brane smooth around 0 here. Okay? So inside the space that compactifies the kink, the brane is a thick brane. But if you look from the outside, it behaves like a thin brane, like the usual Randall-Sumner brane. So you call this the hybrid brane scenario. The lesson is the compact kink does not compactify, say, the geometry. So we study another model with Danilo. So question is for Danilo now, right? Danilo is here. And saying that perhaps we may compactify the brane. So we used those two models in this paper, using the Jacob elliptical functions. The sign, because these functions, they have a nice property. If lambda is controlled by a parameter, lambda is 0, this is the sign. If lambda is 1, this is a hyperbolic tangent. So when you run lambda in between 0 and 1, you go from some trigonometric function to hyperbolic function. So I asked Edith, let us do, because there are some people who do, say, the Simon-Gordon model, the Singer-Gordon model. Let's do everything all together. And we did. And there we noted, we needed this here to make things going well. But this does not compactify the solution. Then we noted, doing the calculation, if you put this factor, it's 1 minus lambda here. So we kind of compactify the geometry too. I will show this to you. Why do I need it? To make things work well. Ask George, how did you find the mixing of timing and the error coordinated to have your nice answer? You didn't show us. You didn't tell us. I will tell you. I will give a step, right? We have a paper that we like it too much. We call it deformation. You take the 5-force model and you construct from the 5-star model. You should read this paper. You construct the 5-6, 5-8, 5-10, every power of phi. Phi 132, it has to be even, okay, to maintain the Z2 symmetry. Okay, we construct. So if you give me a problem, I will try to find a deformation way to get to the solution. So we used it. We started with the sine guard, no, with the 5-force model, right? Sine guard. You take the sine guard model and modified, deformed it using this parameter, okay? And we got this scenario. And this is the kink. I'm plotting here the kink-like solution for the first model. Yes, okay. No, we want to construct first-order formalism. So we start with W. You take the W, so the potential is trivial again, okay? It's not the other way around, which is more complicated. This are the Kinks solution for the first case. And here is lambda for blue. This is the black one is the hyperbolic tangent. Let me. The hyperbolic tangent? No, it's the solution of the sine guard model, which is arctan of exponential or something, the soliton of the sine guard model. So when you vary lambda, you get this way. Red is 1, but 1 gives you a line here. But the line here, we know that the line does not compactify the geometry. So you have to change this. You change it adding this. What we are adding? Remember the kink solution is 5 primes. The derivative of 5 is the derivative of this. Okay? So I asked Danilo, please put in parameter in front that you are controlling the way the derivative goes around 0. Now it's constant in this way. So the solution, now you see red is for 0.9. It's not for 1 more. 0.9, it is plotted 1/20 of the solution. The solution increases very fast. So the response to lambda now is very robust. So you make the kink goes like the sand kink, which is a plus 1 at the infinite. Okay, it's infinite minus infinite, something like this. And this helps us to compactify, say, the geometry, in the sense that this is a standard warp factor for the geometry, okay, with the same numbers here and here. And those are the same numbers here and here for the new scenario. So you see that, in fact, we are not compactifying, okay, because the solution still goes, but it goes very fast to 0, you see? If you compare this with this. Yeah, and we study more things. It goes, the energy density, it goes smoothly. It cannot get 1 because 1 is a singularity there. Okay, but if you go 90.999, it is the same way. It goes the same way. We are now looking for how fermions and gauge fields respond to this. I guess this is my last slide. So, obrigado.